Now, so x squared by a squared minus y squared by b squared equal to 1 is a standard hyperbola whose eccentricity e square is given by 1 plus b squared by a square, right? This is the inside and this is the outside of the hyperbola, right? Now, this kind of a hyperbola is characterized by two kinds of chords. What's a chord? A chord is a line joining any 2 points on the curve. That's a chord, right? That's a chord. For a hyperbola of this kind, where the two branches are separated at birth, there can be a chord of this kind. This could be a chord which joins one point of one branch to another point of the other branch. This is one kind of chord. It's like a bridge between the two branches, right? Right? This chord lies entirely outside the hyperbola. This chord lies entirely outside the hyperbola. This is called an external chord. This is called an external chord. Which lies wholly outside the hyperbola. And there could also be a chord constituted from 2 points on the same branch. 2 points on the same branch. Say for this, these are 2 points on the same branch. And this chord lies wholly inside the hyperbola. This chord is called an internal chord. This chord is called an internal chord. Right? So this time we have two kinds of chords to the hyperbola. External chords and internal chords. And like before, if there is an external chord that passes through the center of the hyperbola, if there is an external chord that passes through the center of the hyperbola, it will always be bisected at the center like any other conic section. C would be the midpoint of PQ. C will always be the midpoint of PQ. If there is an external chord passing through the center of the conic, it will be bisected by the center. C would be the midpoint of PQ always for all conic sections. This time it turns out to be an external chord which when passing through the center of the hyperbola is bisected at the center. This is what happens, right? Now, look, if there are 2 points on the same branch or different branches, does not matter. Same branch or different branches, it does not matter. With eccentric angles alpha and beta. I mean, alpha, beta could be points on the same branch or different branches, does not matter. If you have knowledge of the eccentric angles of 2 points, be it on the same branch or on opposite branches, then P is like, P would have coordinates what? A sec alpha, B tan alpha would be the coordinates of P. What would be the coordinates of Q? A sec beta, B tan beta. So if you know the coordinates of 2 points, can you not find the equation of the line? You can find the equation of the line. So let me tell you the final form without deriving it for you, right? Equation of the chord PQ joining alpha beta. Chord PQ joining 2 points with eccentric angle alpha beta for a standard hyperbola. That's going to turn out to be x by a cos alpha minus beta by 2 minus y by b sine alpha plus beta by 2 equal to sine alpha minus cos alpha plus beta by 2. This is the equation of a chord joining any 2 points. Joining any 2 points. Hmm? Now, suppose the 2 points are on the same branch. Suppose the 2 points are on the same branch. Suppose this point is P. So this is P, A sec alpha, B tan alpha, and this point is Q, A sec beta, B tan beta, right? This is my chord PQ. This is my chord PQ. Whose equation is that? Right? Now, if Q comes closer and closer and closer to P, what happens to the chord PQ? Right. Chord PQ becomes a tangent at P. Becomes a tangent at P. Yes or no? If Q comes closer and closer to P, the chord PQ will become a tangent at P, isn't it? Q coming closer and closer and closer and closer to P, this PQ will be rendered a tangent at P. Right? Yes or no? And if Q comes closer and closer to P, it means what? Beta coming closer and closer to alpha. Beta coming closer and closer to alpha. If beta comes closer and closer to alpha, so if you put beta equal to alpha, you will get the equation of the tangent at alpha. If you plug in beta equal to alpha, you will get the equation of the tangent at alpha. At P, which is A sec alpha, B tan alpha, is obtained by plugging in beta equal to alpha in this equation, right? So this will be like x by A. This will be cos 0, which is 1, minus y by B sin alpha. This will beta equal to alpha. This will be sin alpha, equal to cos alpha. Cos alpha. Yes or no? That's the equation of the tangent at P, right? At alpha, at a point whose eccentric angle is alpha. Now divide by cos alpha, you get x by A sec alpha minus y by B tan alpha equal to 1 is what you get. Yes or no? At a point whose eccentric angle is alpha, the equation of the tangent is, isn't it, if you divide by cos alpha? So x by A sec alpha minus y by B tan alpha equal to 1, right? So x by A sec alpha minus y by B tan alpha equal to is the equation of the tangent at alpha. Angle is alpha. Can I not write this as? So P has coordinates A sec alpha, which is x1, the x coordinate of P, and B tan alpha is y1, the y coordinate of P. So P has coordinates x1 comma y1, right? Yes or no? So x1 is like A sec alpha. So sec alpha is what? X1 by A. Sec alpha is x1 by A, and tan alpha is y1 by P. So I want to find the equation of the tangent in terms of x1 y1. So x by A sec alpha, which is x1 by A, right, minus y tan alpha I write as y1 by B equal to 1 is the equation of the tangent at x1 y1, which is what you expected, isn't it? All that you need to do is replace x square by xx1, y square by y1 to get the equation of the tangent, right? And if there was an x term, what would you do? X plus x1 by 2. A y term, y plus y1 by 2. xy term, half of xy1 plus x1y. This is what you do, right? Recall I told you how to find the equation of the tangent in general. So that's the equation of the tangent at x1 y1 to the standard hyperbola x square by a squared minus y square by b squared equal to 1. And now on, I'm going to use this expression t as xx1 by a squared minus yy1 by b squared minus 1 is my expression t, If x1 y1 is a point on the hyperbola, then t equal to 0 will give me what? The equation of the tangent. If x1 y1 is a point on the hyperbola, this is my x1 y1, and this is my tangent at P. If x1 y1 is a point on the hyperbola, then t equal to 0 will give me the equation of the tangent at x1 y1. Yes or no? Exactly what we did earlier. If x1 y1 is a point on the hyperbola, t equal to 0 will give me the equation of the tangent at x1 y1. How about it? Make sense to all of you, right? Now, the important thing is, this is my hyperbola, and if y equal to mx plus c be a tangent, then this and this will intersect at two coincident points. If this be a tangent to this curve, then they will have two coincident points of intersection. Yes or no? Right now? So for this to be a tangent, if I solve x square by a squared minus mx plus c whole squared by b squared equal to 1, will give me the x coordinate of the points of intersection, will give me the x coordinate of the point of intersection of this line with this curve, right? So now this I can write as 1 by a squared minus m squared by b squared into x squared minus 2cm by b squared into x minus c squared by b squared plus 1 equal to 0 is what I get. This is a quadratic in x. What would it give me? It will give me the x coordinates of the two points of intersection of this line with this curve. But if this is a tangent, then the two x's obtained must be coincident points, must be coincident x's, right? So for this to be a tangent, what should happen? The two values of x obtained must be equal. From this, x1 must be equal to x2, discriminant must be the 0, right? And if you plug in discriminant equal to 0, you get c squared as a squared m squared minus b squared. C will be plus minus root a squared m squared minus b squared. C would be plus minus root a squared m squared minus b squared. That means if C is plus minus root a squared m squared minus b squared, then y equal to mx plus c will be a tangent to the hyperbola, right? So any line of the form y equal to mx plus minus root a squared m squared minus b squared will give me what? Equation of the tangent to the hyperbola. It will be a tangent of slope m. Yes or no? If in an ellipse, do you remember x squared by a squared plus y squared by b squared equal to 1 had tangent y equal to mx plus minus root a squared m squared plus b squared. It's as if, you know, wherever you saw a b squared in an ellipse, now you're replacing it with a minus b squared. In an ellipse, this was plus b squared. Now in a hyperbola, that plus has become minus and this b square has become minus b square, right? Yes or no? Now see, in an ellipse, since it was plus, the quantity inside the square root never became negative. So there was no restriction on m, the slope of a tangent. In an ellipse, there was no restriction on the slope of m. In an ellipse, there was no restriction on the slope of m. But in this case, this number cannot become negative. Not all values of m are acceptable for a given a and b. Not all values of m are acceptable. You know what I'm saying? What are the only values of m that are acceptable? Those values, m is the slope of tangent. Only those values of m for which a squared m squared minus b squared is 0 are acceptable. I'm sorry, greater than 0, greater than or equal to 0. Only those are acceptable values of m. This will give me m squared greater than or equal to b squared by a squared. That means mod m is greater than or equal to b by a. Mod m will be greater than or equal to b by a. That means numerical value of the slope of a tangent must always be greater than b by a. If m is the slope of a tangent, then the numerical value of the slope of the tangent must always be greater than or equal to b by a. Know what I'm saying? That means not all, you will not have tangents of all possible slopes in a hyperbola. This is a condition that must be met. And this condition for tangency is called a basic slope condition. Basic slope condition. This is called a basic slope condition. We'll call it a BSC henceforth. Basic slope condition. Know what I'm saying? Now, the interesting thing is, these are the two branches of the hyperbola. This is my transverse axis, right? I will show that to you in a little while, but for the time being, let me tell you that if C is the center of the hyperbola, there is a tangent of slope B by A. I'm going to demonstrate that later, but for the time being, just accept that from me. There is a tangent of slope B by A. Slope M equal to B by A. And there is a tangent of slope M equal to minus B by A. We will be able to show that these two tangents of slope B by A and minus B by A will pass through the center of the hyperbola, These are two tangents, slope B by A and slope minus B by A. These are special tangents. They touch the hyperbola at infinity. These are special tangents and they will touch the hyperbola at infinity. They will not touch the hyperbola at finite points. These tangents touch the hyperbola, means are tangent to the hyperbola, at infinity. And they pass through the center of the hyperbola. They pass through the center of the hyperbola. They pass through the center of the hyperbola. These lines are lines that are coming closer and closer and closer and closer to the hyperbola. That means, the distance, these are tangents where, this distance between the line and the tangent, this distance between the curve and the line will become smaller and smaller and smaller and smaller as x tends to plus minus infinity. As x tends to plus minus infinity, this length is going to become smaller and smaller and smaller, and it keeps coming closer and closer and closer and closer to the curve as x becomes larger and larger and larger. And these tangents are called asymptotes of the hyperbola, They are called asymptotes of the hyperbola. These are tangents drawn from the center to the hyperbola, and they will touch the hyperbola at infinity. Theoretically, they are not tangents, they are called asymptotes. A line that touches the curve at infinity, would be referred to as an asymptote, It's called an asymptote. Right? Look, This is a line of slope b by n passing through the center. What's the equation of this line? Y equal to b by a into x is one of the asymptotes. Right? This is a line that passes through the center and has slope minus b by a. The equation of this line would be y equal to minus b by a into x. That's the equation of this line. Yes or no? So which means now this is a pair of lines that are asymptotes. Yes or no? So one of the lines is what? X by a minus y by b equal to 0 is one of the lines, one of the asymptotes. Right? This line can be written as x by a minus y by b equal to 0 is one of the asymptotes, a1. So this is a1, one asymptote. Right? And this is another asymptote, a2. I'm sorry, this is a1, this is a2, this is a2. a2 is this asymptote, y equal to minus b by a into x. It can be written as x by a plus y by b equal to 0. Right? Is the other asymptote. A2 is x by a plus y by b equal to 0 is the other asymptote. These are the pair of asymptotes. These are the pair of asymptotes. They touch the curve at infinity. They touch the curve at infinity. And if I want to find the combined equation of the pair of asymptotes, combined equation of the asymptotes if I multiply these two, I'll get the combined equation of the asymptotes is x squared by a squared minus y squared by b squared equal to 0 is the combined equation of the asymptotes. These are lines, theoretically tangents, but really they come closer and closer and closer to the curve at infinity. Yes or no? Right? Now, when I see in general, when I say the slope of a tangent will always be greater than or equal to b, magnitude of the slope of the tangent will always be greater than or equal to b by a. Right? Hey, what does it mean? What's the magnitude of the slope of this line? B by. What's the magnitude of the slope of this? B by. Right? That means any tangent, these are asymptotes now. We'll refer to them as asymptotes, not tangents now. They are like limiting tangents. They are so called limiting tangents. We'll call them asymptotes. Now we'll give them a new name. Any other tangent will have a slope whose numerical value is larger than the slope of any of the two asymptotes. Any other tangent other than the asymptotes will have a slope numerically larger than the slopes of either of the two asymptotes. Yes or no? If the numerical value of the slope of one line is more than the numerical value of the slope of another line, what does it mean? Okay, tell me. This is my x-axis. This is my x-axis, say. I draw a line like this. And I draw another line like this. This has slope m1, this has slope m2. What is the slope of this line? Tan theta 1. What is the slope of this line? Tan theta 2. Do you realize that the magnitude of the slope of this line m2, magnitude of the slope of m2 is more than the magnitude of the slope of m1? Because, right, theta 2 is more than theta 1. Right, so tan theta 2 is more than tan theta 1. Magnitude of the slope of m2 is more than the slope of m1. What does it mean? It means that m2 is more vertical than m1. m2 is more vertical than m1. If the magnitude of the slope of one line is more than the magnitude of the slope of another line, it means this line represented by slope m2 is more vertical than the line with slope m1. This is what it means. Suppose I had, okay, so suppose I gave you two lines like this. By visual feel, tell me, this is line A and this is line B. Which is more vertical? B is more vertical, isn't it? Can you see that B is more vertical and A is flatter? So the magnitude of slope of which of the two will be more? B. If a line looks more vertical than another line, if a line looks more vertical than another line, then the magnitude of that line will be larger. If a line looks more vertical than another line, then the magnitude of that line, magnitude of the slope of that line would be more. Yes or no? So realize magnitude of the slope of the tangent is more than the magnitude of the slope of any of the asymptotes. Magnitude of the slope of any of the asymptotes? Yes or no? B by A is the magnitude of the slopes of both the asymptotes, right? That means the tangent will be more vertical than the asymptote. Tangent will be more vertical than any of the asymptotes. This is what it means. Any tangent will be more vertical than the asymptotes. Any tangent will be more vertical than the asymptotes, than any of the asymptotes. This is what it means. Huh? Which means these are my asymptotes. This is the curve. The point where the asymptotes intersect would be the center of the conic, would be the center of the conic, right? And notice then that if I draw any tangent, this tangent is more vertical than this asymptote, this tangent is also more vertical than this asymptote. Any tangent will be more vertical than any of the two, than both the asymptotes. Right? That's important. That's the basic slope condition. Numerical value of the slope will be greater than B by A. Where B is what? Semi-transverse axis, semi-conjugate axis. A is what? Semi-transverse axis. This is what it means. Yes or no? Can I wipe this off? It's important to understand. That's a basic slope condition for a standard hyperbola. Slope of any tangent will be more vertical than either of the two asymptotes. Physically, it will look more vertical than either of the two asymptotes. Mod m greater than B by A, where m is the slope of a tangent. There was no limitation on the slope of a tangent for an ellipse, or for a parabola, or for a circle. You had tangents of all possible slopes, but here's this curve which is finicky. It says, I'm not going to accept unto me tangents with slopes larger than B by A. And limiting tangents are the asymptotes. These are two lines passing through the center of the hyperbola, and they touch the curve at infinity. Their combined equation is x square by A squared minus y square by B squared equal to 1. Also notice then, if these are my asymptotes, this is the x-axis, which is also along the transverse axis. This is one of the asymptotes, which is y equal to B by A into x. This angle is theta. This angle is theta, right? Theta is the angle that one of the asymptotes makes with the transverse axis. This is my transverse axis, yes or no? Theta is the angle that one of the asymptotes makes with the transverse axis. Huh? Do you realize tan theta is B by A? Tan theta is B by A. And if tan theta is B by A, E squared is 1 plus B squared by A squared. which is 1 plus tan square theta, which is sec square theta. E therefore will be sec theta. E therefore will be sec theta. The eccentricity of this hyperbola, E will be therefore sec theta, right? Hey, the other important thing is, if this is a hyperbola and these are the pair of asymptotes, then the conjugate hyperbola will share the same pair of asymptotes with the hyperbola. Write down. The conjugate hyperbola and the hyperbola. The conjugate hyperbola and the hyperbola share the same pair of asymptotes. Share the same pair of asymptotes. The conjugate hyperbola and the hyperbola share the same pair of asymptotes. Now, this was the transverse axis for this hyperbola. The transverse axis for its conjugate would be this. This is the transverse axis for the conjugate hyperbola, yes or no? That means if E sec theta was the eccentricity of this hyperbola, then this is 90 minus theta. Then sec 90 minus theta would be the eccentricity of the conjugate hyperbola, right? So eccentricity of the conjugate hyperbola would be sec 90 minus theta, which is cosec theta. And do you realize 1 by E squared is cos square theta, 1 by EC squared is sin square theta is 1. All roads lead to Rome. Right? Are you there with me? Right? Also notice, this is the transverse axis of the hyperbola. To draw the hyperbola, it's best to first draw the asymptotes. This is the asymptotes. And this is the transverse axis of the hyperbola, this hyperbola, and this is the conjugate axis of this hyperbola. Conjugate axis of the hyperbola. Right? Transverse axis of the hyperbola and conjugate axis of the hyperbola. This is the center C of the hyperbola, where the two asymptotes intersect and where also the transverse and conjugate axis intersect. This is theta. Do you realize this will also be theta? Henna? Right? That means the transverse axis is one of the angle bisectors between the two asymptotes. Henna? Do you realize the transverse axis is? Write down, the transverse axis would be one of the angle bisectors between a pair of asymptotes. The transverse axis would be one of the angle bisectors between the two asymptotes. Bisectors between the two asymptotes. The conjugate axis, realize, is perpendicular to the transverse axis, so this must be the other angle bisector. So write down the conjugate axis CA. The conjugate axis CA would be the other angle bisector between the pair of asymptotes, would be the other angle bisector between the pair of asymptotes. The two asymptotes need not be perpendicular to each other. One has slope b by a, the other has slope minus b by a, and the product is not necessarily minus 1 always. Right? The two asymptotes need not be perpendicular to each other. When would the two, this asymptote has slope b by a, this asymptote has slope minus b by a. And do you realize the product of the slopes is not necessarily minus 1? Right? Now, if asymptotes are perpendicular, if asymptotes are perpendicular, then the product of the slopes would be minus 1. That's a special case, will not always happen. Product of the slopes of the two asymptotes would be minus 1. Yes or no? Huh? Minus 1, right? So that gives me b squared equal to a squared, or b equal to a. So in this hyperbola, x squared by a squared minus y squared by b squared equal to 1. If b turns out to be a, what happens? Asymptotes are perpendicular. Asymptotes are perpendicular if b is a. What is the eccentricity of this hyperbola? 1 plus b squared by a squared. If b is a, e will be root 2. Eccentricity of such a hyperbola will be root 2. No? And the equation of that hyperbola would be x squared minus y squared equal to a squared. If you plug in b equal to a, you get x squared minus y squared is a squared. That's the equation of that hyperbola. Yes or no? Eccentricity is root 2. B is equal to a. Asymptotes are perpendicular to each other. Such a hyperbola is called a rectangular hyperbola. Such a hyperbola is called a rectangular hyperbola. What is its character? Its semi-transverse axis is equal to its semi-conjugate axis. Its semi-transverse axis is equal to semi-conjugate axis. What is the eccentricity of such a hyperbola? Root 2. Right? That's a rectangular hyperbola. Its equation in standard form is x squared minus y squared is a squared is a rectangular hyperbola. And if you add the coefficient of x squared to coefficient of y squared, it turns out to be 0 in this case. Coefficient of x squared plus coefficient of y squared is 0. See that? That's a rectangular hyperbola. And look, if these two hyperbolas are perpendicular to each other, the slope of this would be plus 1. B equal to a, then this will be plus 1. This would be minus 1. This will then be tan theta equal to 1. So theta would be pi by 4. And E sec theta, sec pi by 4 is root 2. E sec theta, sec pi by 4 is root 2. All roads lead to Rome. Yes, sir. Got me? Another observation. Look, the equation of a hyperbola is x squared by a squared minus y squared by b squared equal to 1 is a hyperbola. Right? Then its pair of asymptotes is x squared by a squared minus y squared by b squared equal to 0. Is the pair of lines representing the asymptotes. The conjugate hyperbola is x squared by a squared minus y squared by b squared equal to minus 1. Check that out. I had written that as y squared by b squared minus x squared by a squared equal to 1. So I could write this as x squared by a squared minus y squared by b squared equal to minus 1. These are conjugates of each other. This is shared by the hyperbola and its conjugate. The asymptotes are shared by the hyperbola and its conjugate. Now notice, and this is critical, Do you realize this expression is the same as this expression, is the same as this expression? Yes or no? These expressions are the same, x square by a squared minus y square by b square. Only the right hand sides differ. And do you see that this is halfway between 1 and minus 1? This is halfway between 1 and minus 1? Yes or no? 0 is halfway between 1 and minus 1, right? This will always be the arithmetic mean of these two. This will always be the arithmetic mean of these two. The hyperbola, even in a very general sense, when I come to it, I'm just asking you to take notice of this. If an expression represents a hyperbola, another represents a conjugate hyperbola, another represents pair of asymptotes, they differ in the right hand side, and for the pair of straight lines representing the asymptotes, the right hand side would be the arithmetic mean of the right hand sides of the hyperbola and its conjugate. That is important. When I get more general, I want you to take notice, make an observation on this, make a very simple observation. This number would be halfway between these two numbers. Makes sense to all of you, right?